Hey guys, Dr. Mandis here. I'm just trying to talk to you today about oxidation numbers. It's a little bit of a confusing topic, but it's a necessary topic. Oxidation numbers gets used for charges and for parent charges. It's also called oxidation state. So instead of number, you got state, and people like oxidation state because it sounds fancy. But oxidation state, oxidation number, same thing. It can be the charge or it can be the apparent charge. Okay? Now sometimes sharing isn't always equal. Okay? So say you have like an SO2 ion and an SO2 ion. I need a big fat pen here. Cool. And SO2, you got a molecule, I should say. You have S double bond O double bond O. Cool. In that molecule, the whole thing is neutral, definitely neutral. But if you look at oxidation states, oxidation numbers, sulfur acts as if it's like a +4. Notice how it's not 4 positive. +4. HO is like a -2. And what that tells you is at the butt ends of the molecules, you got a seed of negativity, and in the center, you got a seed of positivity. All right, which matters in some chemical reactions depending upon what you want to do. All right, but that's how you can get apparent charges inside a covalent compound that doesn't have charges. But sometimes you have ionic compounds, ionic ions, or whatever it is, and you have charges, and these are the oxidation numbers. All right, so like in the tin that we have there, it's a 4 positive. Well, the oxidation state is going to be +4. Okay, and God, man, why is my pen so skinny? And the copper here is definitely a +1, +2, +2. These changes in oxidation state reflect oxidation and reduction reactions. And they're kind of easy to see those oxidation numbers. Most students can kind of grab that. The problem is when you have things like permanganate or another neutral molecule like MnO, I should say compound, when you have those neutral compounds, what do? How do you get the oxidation states out of that jazz? Well, you have oxidation rules that help us out with all of this stuff. Okay, there are a handful of rules, and they're not so bad. Okay, rules for assigning oxidation numbers. First off, group 1, okay, group 2, most of group 3. Okay, you won't really see that anywhere because talum's the only exception. But group 1 is always going to be a +1. Group 2 is always a +2. Group 3 is always a +3, except for talum. Okay, but for the most part, that matches the trend for charge you learn in high school chemistry. The question is about all of these guys and those folks. Okay, what do you do about all of that? All right, well, there are rules for that too. Okay, for the next one, we got fluoride's always a -1. Well, fluoride's right over here. Fluoride's always a -1, and that matches what you learn in high school chemistry, but not the rest of this column. Okay, not the rest of it. Okay, only fluoride's a -1. The other guys really depends upon whom they're with. Okay. Oxide is another one. O's right here. For the most part, he's a -2. Okay? So it matches the trend. -2, -1. But not these guys down here. They're too big. They have d orbitals. Things change. Okay? Sometimes you'll see oxide in a peroxide or something like that, in which case it's a -1, but it has that little pattern of H2O2, Na2O2. And for the very rare case, it could be a +2, like OF2. But for the most part, 9 times out of 10, -2 for O. It's a very handy thing to know. Okay, H is always a +1. If it's the cation, if it's an anion, it's -1. A lot of you guys at this point where H is right there. A lot of you guys at this point are probably saying, when's H ever an anion? You get up things like calcium hydride, sodium hydride, okay? Where H is clearly in the anion part of that ionic compound. So in those cases, he's a -1. But again, just like oxygen, 9 times out of 10, +1. Okay? Now here's a kicker. Sum of all the oxidation numbers equals the overall charge. Very, very, very handy little rule to know. Okay, kind of like in the CaH2 I just wrote. Okay, calcium is a +2. Okay, H is a +1. From the positions on the table, calcium's a group 2 atom, H is group 1. So, in this case, H is -1. Okay, so if you look at that, you got calcium as a +2, 2 hydrogen's a -1. If you do the math on that, +2 times -1, you end up with a total of 0. And lo and behold, hey, that's the charge up there. They're 0. The individual ones always add up to the overall charge. So let's look at some better examples there, okay, of this kind of stuff. If you look at it, you have N2, Na1 positive, NH4 1 positive, SO3 2 negative. For N2, you would say, hey, I got 2N adding up to a charge of 0, so each n must be 0. Well, that's handy. And if you look at some places, they'll talk about singular elements of a charge of 0. It's just easier to know the charges, whatever it is. If you have a singular ion, the charge is the charge, because, I mean, you'd have 1 Na would equal the charge plus 1. So if you had, like, say, a copper 2 ion, well, its oxidation state plus 2. If it's the charge, it's the charge, N3 negative. Oxidation state minus 3. Singular ion, easy enough. It is the charge. That's where oxidation number and charge sort of get confused, because sometimes it is the charge. But in NH41 positive, what's the N? What's the H? H is always a plus 1, unless it's in a hydride, and it's not. So you have an N plus 4 H's are adding up to plus 1. Okay, well, N plus 4 H's add up to plus 1. Well, the H is a plus 1. So basically, if you continue out that algebra, you have N plus 4 equals plus 1. That means the N has to be minus 3. Alrighty. A lot of people short circuit this and they just sort of write on top of the thing. That's kind of what I'll do on the SO3 2 negative. SO3 2 negative. You know O is minus 2, except in peroxide, blah, blah, blah. But each O is minus 2. So you look at this and you write, either 3 times minus 2, or you just write minus 6 up there if you're the student. Okay. For the sulfur, then you're trying to figure out, hey, what here plus that will equal minus 2. And if that doesn't float, S plus minus 6 equals minus 2. That means S has to be a plus 4. Okay. A lot of students, once they get kind of practice with this, will just write on top of it, because picture like a chemical equation. You kind of just want to look at each one individually and short circuit that a little bit. Okay. Sometimes you're going to get an example like FeCl3, and you're not going to know either one. You don't have a rule for either of them. But you do know that ionic compounds dissociate. So if you're given an ionic compound, just dissociate that puppy, okay? And binary ionic compounds dissociate the cation and the anion, and you get the oxidation number. So FeCl3, we can dissociate to iron 3 plus chloride, okay? And in that case, then you'd say iron is in a plus 3 oxidation state, chloride is in a minus 1, okay? For those of you guys tell me about chloride, it's not always going to be minus 1 like a halogen. If you had like ClO4 1 negative, okay, then chlorine would be, I don't know, you have 4 O's at minus 2. That's negative 8 for the O's. What here plus the negative 8 will get you to negative 1 plus 7, because plus 7 minus 8 gets you to minus 1. Anyway, that's just a quick little gig I wanted to do on oxidation numbers. See if that helps you out in calculating them. Probably spent too long in it. Anyway, this is Dr. Mandis. I'll talk to you later. Take care.